For set theory, I cannot recommend any one textbook, because we are not going to do either naive set theory or axiomatic set theory. It will be a mix of them. So if you read axiomatic set theory textbooks, then they will be too formal, and naive set theory textbooks will be too informal. Yeah, so none of them will suit the purpose. So instead of that, just attend the lectures properly, take notes, study from them, and solve all the tutorial problems. Yeah, hopefully you have all seen the tutorial sheet as well. Right. So last time we started with this, yeah, that there is the concept of a set is currently undefined. Yeah, until we study logic, this will remain undefined. What we can do is we can assume the existence of the empty set, and from that empty set we can construct natural numbers, yeah, which we called omega last time. That's von Neumann natural numbers. That V in von Neumann is actually F, because it's German. And there is no distinction between sets and elements. Okay, so we are used to that kind of thing. Yeah, A is a set, and then X is an element, small x is an element, so there is no such distinction. And before we proceed with how to construct new kinds of sets from the existing ones, I want to confuse you even more. Yeah, that's usually the thing that confuses everybody. It has confused mathematicians for several years. So suppose, I'm going to tell you a story. There is a small village, yeah, in the middle of nowhere. People there don't know anybody outside, and outside people are not aware of their presence in that village. Now there is only one barber in that village. So you know barber, yeah, who cuts hair. So this barber has a rule, yeah, very principled man, that he will only shave those men who do not shave themselves. Okay, so if there is this person, he is the barber and he is one of the villagers, then if he doesn't shave himself, then the barber will shave him. If he shaves himself, then the barber won't shave him. So that's his principle. Now the question is, who will shave the barber? Huh? Nobody can? Yeah, if nobody shaves him, yeah, if he shaves himself, then by his principle he is not allowed to shave himself. And if he doesn't shave himself, then his principle forces him to shave himself. You understand? This is called Barber's paradox. Right? So there is something similar in set theory. It's called Russell's paradox. So let me write that down. So that a set is normal if n is not an element of itself. Okay, now please pay attention, yeah, to every single word I am about to say. Let us say that a set n is normal if it is not an element of itself. Now consider the set, let S be all those n's such that n is normal. Okay, let me write it again. All those n's such that n is not an element of itself. Now this is a kind of reformulation of Barber's paradox. Now the question is, does S belong to S? Yes? What are you saying? Yes or no?
So if it's like paradox. If it belongs, then it should not.
Correct. It's a paradox that if S belongs to S, then by the defining property S is not normal. So S shouldn't belong to S. On the other hand, if S doesn't belong to S, if S is normal, then it should belong to S, so that S fails to be normal. You understand? Now, how is this paradox resolved? I asked you to be very attentive.
So can you please repeat what you just said about this paradox?
Sure. So, say that you understand the definition of normal, right? So, if S belongs to S, then what is the property of belonging to S? That S doesn't belong to S. And if S doesn't belong to S, then S should belong to S. So, how can we resolve this paradox? Any ideas?
Sir,
Yes?
by introducing the new axiom,
What kind of axiom?
certain kind of sets are not allowed.
Certain kinds of sets are not allowed. Yes, that's correct actually. So, S, according to Zermelo-Fraenkel's set theory, S is not allowed to be a set. So, I will give you something. So, there is something called axiom of regularity in ZF set theory. States, it doesn't really state this, it's a consequence. It states that each set is normal. Okay, so the set doesn't belong to itself. No set belongs to itself. Otherwise, we'll get a decreasing sequence. Yeah, this is a set A. Then A is an element of A is an element of A is an element of A. Well, there is another name for this. Yeah, I will also write that. It's called axiom of foundation. Right, I am not going to state axiom of foundation at this moment, but it implies that no set can belong to itself. And there is also a provision. The collection of all sets is not a set. It is called a class. Okay, so class is a term which is again not defined. Okay, so there is a distinction. So there are certain, so classes can be sets or they may not be sets. So classes are partitioned into two subclasses. One is of proper classes and another one is of sets. Okay, so proper classes and sets, that's our distinction. So the collection of all sets is a proper class. So therefore there is no question of asking this. It's not a set. Understood? So that's how we resolve paradox. Resolution of paradox means we don't let it arise. Right? So I will write it on the next slide. So classes are either sets or proper classes. So these are two different categories. So given any set, any single set, you can always construct the singleton set, correct? So there is something called axiom of pairing. So axiom of pairing implies that given a set A, there is a set X whose only element is A. Yeah, which means X is equal to singleton A. This is nothing new for you. Yeah, i.e. X is equal to singleton A. That means, yeah, as a consequence, every set is an element of some other set. Do you agree with this? Yeah, every set is an element of some other set. So therefore, that is how we set distinction between sets and proper classes. So a class X is a set if there is some class Y such that X belongs to O. Y.
Sir,
Yes.
it could be set or class.
Where?
In this a class that is a set if there is some set by.
No, there is some class.
So belonging, you have not defined the belong nature.
Belonging, yes. So like for example, the collection of all sets is so large that it doesn't belong to anything else. Right? So therefore, we just say that X is a set because we are trying to define a set amongst classes. So we cannot use the word set in its definition. Okay, a set, a class is a set if it is an element of some other class. Otherwise, it is called a proper class.
So here Y will be a proper class or a set?
Now that depends on Y. Yeah, so we are not saying anything about Y. Who asked the question? Yes. So we are just saying that X is a set if it is an element of some other class. That's all. And if it is not an element of any other class, then it is a proper class. Why am I writing all these things? Yeah, too much philosophy is not good. Yeah, you are just second year students right now. But when we write some expressions like this, so yesterday we saw this union thing, right? A union B. If A and B are two sets, then A union B was defined to be the collection of X such that, can you tell me? X belongs to A, or? Now the question is, where is this X coming from? So we are choosing it from the class of all sets. I just wanted to say that statement. That's why I said this Barber's paradox, Russell's paradox. Yeah, we are choosing X from the class of all sets. Yeah, because X is not coming from any universal set. We are actually talking about the universe of all sets. Yeah, which is a proper class. Okay, let's go ahead. Can you tell me what is A intersection B? X such that X belongs to A.
And X belongs to.
Now you can observe that we are again using certain axioms while defining this, and those axioms are hidden inside these words. The words or and, they are part of our understanding, human understanding, which in logic is called semantics. Right? So all of us have exactly the same understanding of the words and or, if then, if and only if, right? So there is no distinction between our understanding. So that's why when we write this, we think that we know these things, correct? The left hand side is abstract notion, but we think that we are explaining it using the right hand side, the words like and or. See, when I'm saying and or, I'm using that middle and again, right? So we understand language, so in terms of language we are explaining something, and that's not going to change. Yeah, yes, the set theory that you know is not going to change. I'm just trying to encourage you to ask more questions, that do you really know the things that you feel you know? Okay, any other operation of sets? Subtraction, yes. So set subtraction, right? So A minus B, what is it? All those x's such that x belongs to A and x doesn't belong to B. Very good. Any other operation? A triangle B. Okay. A triangle B is the symmetric difference operator, right? So what is the definition? X such that what? You know symmetric difference? No? It is A minus B union B minus A. So that means exactly one of x belongs to A and x belongs to B holds. Yeah, I mean this is, in other words, it is simply A minus B union B minus A. Any other operations that you know? I'm waiting for one particular thing. Complements, yes, I was waiting for that. How, like with respect to what? Complement with respect to what? Complement with respect to a class, that will be a proper class, so we don't want to define it. Right? If from the entire universe of sets, you just remove one set, then it's still not a set. It's a proper class, so therefore we don't define it. Yeah, so the notion of complement was introduced to you because you were working locally. Locally means there was a universal set and you are working inside it. And that's why you could do that. But there is no notion of complement. The complement is replaced by an appropriate notion of set subtraction. Yeah, what you were calling complement was really the universal set minus your set. Okay, any other thing? Any other operations on sets, like the way you can get new sets from existing ones? Cartesian product, yes, very interesting concept. So what is Cartesian product? A cross B? Don't be so afraid to talk, yeah, I mean you know these things. The pairs x comma y, right? X comma y such that x belongs to A and y belongs to B. Very good. What is the meaning of this pair? Everything we are doing is a set. Yeah, I mean on the first slide I wrote that there is no distinction between sets and sets and elements. So what is this symbol? Bracket x comma y. It is a point. What is a point? It is a tuple. Okay, what kind of tuple?
It's a connection between two elements of two different sets.
It's a connection between two elements of two different sets. What kind of connection? Huh? It is a mapping. Mapping between what and what? Set A and set B. No, I mean we are choosing arbitrary elements. I am asking you, what is the meaning of that bracket? So there are two types of pairs. Yeah, I mean this is a pair that you all agree. Is it an ordered pair or an unordered pair? Ordered pair. Very good. Now that is set. So how do you define an ordered pair? An ordered pair, yeah, not unordered pair. An ordered pair using sets. Can I mean definitions, yeah, possible definitions for ordered pairs. Give me some choices. Can I use not A, yeah, we are trying to use xy equal to xy. Will this work? Why doesn't it work?
We need to differentiate x, y and y.
We need to differentiate between two elements. Yeah, it's an ordered pair. So the first element and second element, especially if they are different, then we need to distinguish between them. So we need to do something different. What else can we do? Can we do this? We can do this. Is there any so xy and yx, will those two ordered pairs be different or same with respect to this definition? Same. So this is also not useful.
You can do like x0 and y1.
X0 and y1, very good. How should I write x0?
Like x and then the null set. Like a set with x and the null set.
What does that mean? Okay, you are saying this?
Yeah.
X comma null set?
Yeah, and then it should be another, like it should be a set.
X comma null set and another set, right?
Yeah, and then like y comma 1.
Okay, so this is your definition. What will happen if x happens to be 1 and y happens to be 0? You understand? If it is 1, then this is 1 comma 0, this is 0 comma 1, and then you are not really distinguishing between the ordered pair 0 comma 1 and 1 comma 0. So this also doesn't work. It's such an interesting concept, right? We always use coordinate geometry. A point on the plane is 3 comma 4, but do we really understand what is 3 comma 4 as sets?
Like instead of 5 we can write another set consisting of 5 comma 1.
Another set consisting of 5 comma 1. Yeah, you are just getting trapped into that rabbit hole. Yeah, it's not going anywhere. Any other idea? Yes.
You can take a set with two elements, one being x, and the second being the set containing x and y.
Set containing x and y. Yes. Okay. One is x and the second containing x and y. Will this work? There don't seem to be any objections, not that we are in a court. Okay, so Kuratowski's definition is quite close to this. Yeah, so Kuratowski defined. We are going to look at lot of Polish names. Yeah, Kuratowski is a Polish name. So defined xy to be equal to the set consisting of two different elements, namely this. Yeah, so we will always follow this. In fact, after this discussion, we will never ever talk about ordered pairs again. Okay, but you need to know this. So this definition actually helps you to understand the first component. What is the first component? X. So yeah, I know it's x, but how to obtain it from the right hand side?
Subtraction.
No, cardinality 1 is not really the right answer. It is the set which belongs to both of them, both of the elements. Right? The right hand side is a set consisting of two elements. in general. Yeah, if x is equal to y, then nothing will matter. If x is equal to y, then the right hand side is singleton x and singleton x. So therefore everything will be singleton x. Okay, so in that case we understand that both elements are equal if there is only one element. Whereas if there are two elements, then the common element of both the elements is our first component, and the not common element, which only belongs to one of them, is the second component. So we can extract information back. Right, so this is a good definition, and we'll stick with that. So now we understand Cartesian products. Cartesian products are the sets which consist of such elements. Yeah, the elements are these pairs, ordered pairs, and the ordered pairs are written like this. Any confusion about this? Yes? Last line? That's a definition. When I say colon equal to, that's by definition. So Kuratowski defined it to be, what did you not get? Yeah.
So what the x and xy?
It is the set consisting of two elements. The first one is singleton x, the second one is x comma y. What is the purpose of this? Because we want everything that we talk about to be a set. So therefore from this you can obviously get the first coordinate and the second coordinate. First coordinate is the element which is common to both the elements, right? And the second coordinate is the element which is not common. Yeah, it is only an element of one of the elements but not of the other. Right. So this is Kuratowski's definition of ordered pairs. So we have also covered Cartesian product. Any new way of generating sets? If I am just given one set, can I?
Some subset of a given set.
Right. Now I was also waiting for this. Yeah, subset of a given set. However, a subset is not a well-defined quantity. So when do we say? Yeah, so the question is, what is the meaning of A subset equal B? Can you tell me?
A intersection B is same as
A intersection B is same as A. Okay, yes, well that's also a tutorial problem. Yeah, try to prove these things are equal. So the meaning of subset is for all x belongs to A implies x belongs to B. That is the meaning of subset. Yeah, the elements of A are also elements of B. But even though a single subset, yeah, one more thing before we proceed, yeah. A subset equal B is the notation we'll use for subset, and A proper subset of B. Yeah, this is the notation we will use. So this means
there exists some x for which.
Yeah, it is equivalent to A is subset of B, but A is not equal to B. Yeah, that's also a simple way of saying that these two sets are not equal. So please don't use, yeah, this is a confusing symbol. Yeah, do you mean proper subset or do you mean improper subset? It's never clear. So therefore we will always distinguish by either subset equal or subset not equal. Okay, simple thing. However, now using subsets, we can construct one set, the collection of all subsets of a given set. What is it called? The power set. Okay. So power set. So P of A. What is the definition? All those x's such that x is a subset of A. Very good. So that is our power set. So power sets are definitely larger than set any given set, and we will see very soon we'll see the definition of the theorem which states this, that you cannot, Cantor's theorem, which says that power set of A definitely contains more elements than the set A itself. However, like to formulate that Cantor's theorem also, we need the concept of a function. So I think we discussed this enough yesterday. A function is a triple. Yeah, a function f is a triple A, comma B, comma yeah. So can you replace f with something more meaningful? I mean, okay, I will write f, but equivalently A, comma B, comma a subset graph of f, which is a subset of A cross B. Yes, every function has a graph, correct? So, and a graph is a subset of the Cartesian product, that's also clear? Okay, so this is what we need, which satisfies, what property should it satisfy? For all x in A, there exists a unique y in B such that x comma y belongs to the graph of f. Well, I should be more precise. What is the meaning of there exists unique? So I will write that down. So for all x in A, there exists a y in B such that x comma y, the ordered pair x comma y belongs to graph of f, and whenever y1 and y2 are two different elements, and for all y1 and y2 in B, if I say that x comma y1 belongs to graph f and x comma y2 also belongs to graph f, then y1 is equal to y2, and I should put a bracket around this. Yeah, that is the meaning of there exists unique. Right, so in normal language we are just choosing a domain, so this A is called the domain of f. Then this is the codomain of f, and there is a graph. So now a function has become a triple consisting of two sets and a subset of their Cartesian product which satisfies certain properties. So how many functions can there be? Between A and B, how many functions can there be? I am not asking for the size, but I am asking if it is still a set. Observe this. Every function is in bijection with the collection of graphs. Right? I mean, the set of functions is in one-to-one correspondence with the set of graphs. Now, graphs are subsets of A cross B. So, therefore, how many, at most, how many functions can there be? As many subsets of A cross B. So, therefore, every graph of F is actually an element of the power set of A cross B. And therefore, the collection of all graphs is an element of the power set of the power set of A cross B. So, still it is a set. Understood the argument? No? I will repeat. Graph of F is an element of the power set of A cross B. Yeah, because it's a subset. That's how we define power set. Yes, all subsets are elements of the power set. Right. So, graph of F is an element of the power set of A cross B. By the way, I will randomly switch between capital letters and small letters. Yeah, don't mind that. Everything is a set. In set theory, everything is a set. So, so therefore, now graph of F is an element of power set of A cross B, and therefore the collection of all such graphs is a subset of power set of A cross B, which means it is an element of its power set, the power set of A cross B. So therefore, by you remember that we said over here a class is a set if it is an element of something. Okay, so we have already got that. So let me write it down. The collection of all functions from A to B is a set and is denoted by fun AB, yeah, because we are going to have fun, yeah, or B to the power A. Okay, that's also another notation. Actually, there is a lot that you can play around with. Yeah, I mean, I'm sure you have done this. So, if B and A happen to be two finite numbers, let's say 3 and 2, then how many functions are there from 2 to 3? Precisely 3 to the power 2. Yeah, because for every element you are choosing one image. Right, so therefore this notation is consistent with exponentiation. When you take the size of B to the power A, it is size of B to the power size of A. I'm just not going to write it because we haven't defined size. Okay, soon we will define size, but that's why the notation is there. Yeah, but both notations are useful. So this is yet another way of constructing a new set from existing sets. If A and B are sets, then fun AB is also a new set. Okay, so there are some spatial types of functions. What are they? I mean, you gave me list of functions yesterday, but I'm not asking about those types of functions, like theoretically important classes of functions. Bijective can be broken down into two. Okay, so we will write a function. Yeah, so how to write a function. I'm sure you know this, but writing is an important skill, so I will explain the difference between these two arrows also. So f is a function from a to b, we write colon and then arrow, whereas this arrow at the bottom, x maps to fx. Yeah, at some point you should also start learning LaTeX, and in LaTeX the code is actually just backslash maps to, right? This is to this arrow, and this arrow is maps to. So in your writing, try to incorporate these two different types of arrows. What this says, yeah, this is x is going somewhere, whereas a is not going anywhere. Yeah, this doesn't say it's going anywhere, it's a rule from a to b. Okay, so these two are different types of arrows. Okay, so a function f, from a to b is, let us do 1 1 first. What is the formal name for 1 1 functions? Injective. Very good. Is injective function if what happens?
For every x belongs to A, there exists a unique y.
For every x in A, there always exists a unique y in B such that x comma y is in graph. So that's the definition of a function. Please don't confuse that.
And vice
Every
versa.
y
And
there
vice
is a
versa.
unique x.
For every y, there exists a unique x such that fx is equal to y. That says it's a bijective function. We are not asking for that.
x1 equals x2 implies and implied by f of x1 is equal to f.
Exactly. If for all x1, x2 in A, f of x1 is equal to f of x2 implies x1 is equal to x2. Actually, the other side is obviously true. If x1 and x2 are equal, then there is a unique image. So therefore, we can also put a backside, but we never have to check the other implication, right? We only check that given two elements, are they going to two distinct elements should map to two distinct elements. That is the injective function, or it's also called 1 1, right? 1 1 function. Okay. So a function f is surjective if what happens? Somebody from the back, nobody speaking there. You don't know what a surjective function is?
For every
For every y belongs to B, there exists
If for all y in B, there exists a
x belongs to
x belongs to A such that f of x is equal to y. Very good. Oh, you are not answering because the answer is too easy. Sometimes you don't answer because it's too difficult. And what about bijective?
both the condition.
Okay. If for all y in B, there exists a unique x in A such that fx is equal to y. Yeah, so bijective is clearly injective plus surjective. Okay, so in last 5 minutes we'll just spend some time looking at examples. So give me some example of an injective function. It's simple. Fx equal to x. Again, from where to where? That's the problem. Don't say these things. That's what you are supposed to learn. From real numbers to real numbers. Okay. So f from R to R, which is given by the rule that x maps to x, is is injective, surjective, everything. Yeah, this is identity. Real numbers also don't matter, is bijective. Okay, second example. Something which is injective but not surjective.
Fx equals to x square from 1 to
Fx equal to x square, okay. We only know real numbers. Although in this course we are also going to construct real numbers from natural numbers. Yeah, from naturals to integers, integers to rationals, and rationals to reals. We are going to do that step by step. So right now I am just taking your word that you know real numbers. Because it said that God gave us natural numbers, everything else is man-made. Yeah, so we have to construct everything from naturals. Well, God gave us not just naturals, I mean God gave us only the empty set and everything else is man-made. We are weird, yeah? We create everything from nothing. That's how the story of the Big Bang Theory also goes, yeah? There was nothing and then there was an explosion, everything was created. So this is what? This is bijective? Okay, so that's why I wrote this. Yeah, this is neither injective nor surjective. Can you give me a function from natural numbers to natural numbers, which is injective but not surjective?
So this map only but
N to N square.
This map from n to n, okay. So n to n. And please remember, natural numbers do contain 0. Yes, I'm going to say that all the time. Is injective but not surjective. Okay. So in this case, what is the image of f?
Set of all perfect square.
It is the set of all those y's in n such that there exists an x in n such that y is equal to x square. Yeah, he gave me the answer and he is not happy because I just butchered his simple enough definition. We can also use this, yeah, 0, 1, 4, 9. However, this particular thing is misleading. Yeah, sequences are very misleading. There, you expect the next term to be something, but it could be an entirely different sequence. So therefore, it's not really a good way of writing things. Okay, so this is image of f. It is injective but not surjective. Any function which is surjective but not injective, x maps to sin x.
From
That is surjective.
0 to
10x
0 to pi. But
0 to pi.
yeah, 0 to pi and 0.
Okay, we are going complicated. How about real numbers? To 0, 1. Minus 1, 1. Yeah? X maps to sin x. This is surjective but not injective. Okay, so in tomorrow's class we will define what is a finite set, and we will also look at some other things associated with functions like direct image of a subset and inverse images of subsets. Yeah? I mean, once we get to this point, you all might feel the course is very easy. The first lecture was too difficult, the second lecture is too easy. Yeah, so, but it will be a balance between things. Philosophically, you will have to think a lot, but not much is happening as far as sets are concerned. Yeah, you all know these things. So there was an important topic which we missed while studying sets and functions, and that is called the image factorization of a function. It's something very simple, but for the sake of completeness I have written it on the board. So suppose f is a function, then it can be factored as a surjection followed by an inclusion. Yeah, notice that I am not saying injection, I am being more specific. A surjection followed by an inclusion. Inclusion always corresponds to subsets. Okay. So what is that? I mean, I have drawn the picture here. You look at a function f. Yeah, I mean, we can say that f can be written as h composed with g, where g is a surjection and this is inclusion. So this is my g and this is my h. The surjection part is simply the co-restriction of our original map. Co-restriction means restrict the codomain and you make it as small as possible. Okay. So we make it as small as possible means we land inside the image. So A to GA, what is the rule G? X maps to f of x, yeah, it doesn't change. So this is the co-restriction of our original map f, and the inclusion part is inclusion of the image inside the codomain. That's all. Yeah, very simple thing. So one simple example is given sin x as a function, x maps to sin x as a function from reals to reals. What do? We factor it as, yeah, I mean this is sine function, this is also sine function, and this is simply inclusion. We go to its image, the image is the closed interval -1, 1, and then you include that. So this is called image factorization.